For question 1, find the difference quotient. The way it was suggested to start this problem is to figure out first what this expression is, f of x plus h. So what I recommended is if your input into a function is something other than just a simple numerical value, then I would recommend that you rewrite the function, but remember, whenever there is a variable, leave that as an empty parenthesis, and that empty parenthesis gets filled in with whatever input is right here. So now we simplify x plus h to the second power. That's x squared plus 2xh plus h squared. Then distribute the 3. So this is f of x plus h. So that's going to go on the top left part of this difference quotient. Now, the top right part of this difference quotient, we need to subtract the original function. So subtract the entire original function. So I'm going to do that in a parenthesis, and then it's divided by h. Now this negative sign is going to be distributed to both terms. So that becomes negative 3x squared and a positive 1, which means that positive 1 is going to cancel with that negative 1, and this negative 3x squared will cancel with that positive 3x squared. So the terms left in the numerator are 6xh plus 3h squared divided by h. And we can factor out the greatest common factor between these two terms is 3h, but since there's only a single h in the denominator, I'm just going to factor out a single h from the numerator. So I'm going to factor out h, leaving 6x plus 3h. So now those can cancel out. So the result of simplifying the difference quotient is 6x plus 3h. Okay, for question 2, to find the inverse of a function, remember you switch the place of x and y. So we have x, and really this is y. So for part A, if we switch those places, and then we need to solve for y. We need to get y by itself. So if we solve this like we would solve an equation, we'd have to subtract 3 first, then divide by 2, then get rid of the square root, and finally the last thing we would do is add 1. So we're going to do things in that order. Subtract 3, then divide by 2, now we can square both sides. And last step here would be to add 1. So we would end up with the inverse function as this quantity squared with a plus 1 on the outside. For part B, start the same way. We'll switch the place of x and y. And now we want to undo this fraction here, so we multiply both sides by the denominator. So then we'd have like that. Now here we can do this one of two ways. We can either distribute the x to get rid of the parenthesis, or we can divide the x over to the other side. So that's what I'm going to do. I'm going to divide x like that. And then last step there would be to subtract 3. So then our inverse like that. So we're graphing a function here that's a quadratic function, so it's a parabola, and it says to use transformation. So there's a transformation here, 1 unit to the right, and then 2 units up. So there's the vertex, 1 unit to the right, 2 units up. So there's the vertex of the parabola. Now here is a vertical stretch, and then we have a reflection, a vertical reflection. So the parabola is facing upside down. So at this point, once you have the vertex, what I recommended is you just plot a few additional points with x values that are near the x value of the vertex. So if the vertex has an x value of 1, I would just plot either 0 or 2 for x. So if x is 0, we have 0 minus 1, which is negative 1. Squared is positive 1. Positive 1 times negative 3 is negative 3. Negative 3 plus 2 is negative 1. So 0, negative 1. And then using symmetry, we can plot a point over there. And there's our parabola. Question 4, we are combining functions. For part A, we're subtracting the two functions, and for part B, we're finding a composition f of g of 3. So for part A, this is f of x subtract g of x. So we have f of x minus g of x. Which is just x minus 4 minus 2x squared minus 1. So if we combine some like terms, we have a negative 2x squared, a positive x, and a minus 5. For part B, we have f of g of 3. So the 3 as an input is an input for just the g function. So I'm actually going to take this part out, g of 3, and do that first. So g of 3 is 2 times 3 squared plus 1. 3 squared is 9, times 2 is 18, plus 1 is 19. So g of 3 is equal to 19. So this g of 3 can be replaced with 19. So instead of f of g of 3, we replace this g of 3 with 19 because they're equal to each other. So now we have 19 as an input into the f function. So the f function is input subtract 4, and the input is 19. 19 subtract 4 is 15. All right, question 5, part A. To list all the possible rational zeros, remember that's the P divided by Q theorem, the rational zeros theorem. So the list for P are factors of that number there, and then the list for Q are from the coefficient in front of the leading term, which in this case is 1. So the factors of 30, plus or minus 1, 2, 3, 5, 6, 10, 15, and 30, and then for Q, it's just plus or minus 1. So then the real list we need is P divided by Q, which since Q is just equal to 1, if we divide each of these numbers by 1, then we're just going to get each of these numbers here. So this first list here is our P divided by Q list. So I'm just going to make a little adjustment here. This is P divided by Q. So that's the list of possible rational zeros. Now for part B, to find the zeros of this polynomial, we need to start with this list of possible rational zeros and do synthetic division. So we start with 1, positive 1, and then for synthetic division, remember we're just using the coefficients of each term, and if there's a term missing, we have to put a 0 in its place. So remember these numbers are just the coefficients from here. And we do the synthetic division algorithm. Okay, doesn't look like positive 1 worked. So try negative 1. All right, doesn't look like that's working. So we can try positive 2. All right, positive 2 worked. So what we have, remember with this result, is we know that x equals 2 is a 0, and this are the coefficients of the other factor. So if x equals 2 is a 0, remember that means x minus 2 is a factor. And then these are the coefficients of a third degree polynomial because we started with a fourth degree. So it's going to be x cubed plus 5x squared plus 11x plus 15. So now we need to continue doing synthetic division from our list of possible zeros because we are not to a quadratic, we're at a cubic. So I'm going to continue doing synthetic division now on this reduced polynomial. So I've already tried 1 and negative 1 didn't work. We know that 2 works, so I'm going to skip over to negative 2 now. With this reduced polynomial coefficients 1, 5, 11, and 15. Okay. Negative 2 did not work. Let's try 3. 3 is not working. We can try negative 3. All right, there we go. So now I'm going to take, and we still had x minus 2 as one of the factors. Now we know that x plus 3 is one of the factors because that turned out to be one of our zeros. And then these are the coefficients of a second degree polynomial, x squared plus 2x plus 5. So now that we're down to a quadratic expression, we can either try to factor it or use the quadratic formula. This does not factor. So we're going to use the quadratic formula. So 4 times 1 times 5 is 20. This is 4. So 4 minus 20 is negative 16. That turns out to be negative 1 plus or minus 2i. So the zeros were x equals 2 from this step, and then x equals negative 3 from over there, and then x equals negative 1 plus or minus 2i from that step there. Now for part C, they want us to write p of x in factored form, but it says factor it into factors that are linear or irreducible quadratic. So like this is a linear factor, this is another linear factor, but this quadratic factor didn't factor any further. We had to use the quadratic formula. So they actually, this is what we're looking here for part C. The two linear factors, x minus 2, x plus 3, combined with the quadratic that's irreducible. So this is the answer for part B. Here we go. This is the answer for part C. Question 6, we need to build a polynomial now that satisfies these three criteria. It has to be a degree 3, it's got to have these zeros, and we'll get to this one in a second. So let's start with the zeros. If it's degree 3, it should have 3 zeros. So in part A, there's purposely one missing. Remember that kind of a fact, 0, 2 minus I, always comes in a pair, so that we know there's a missing factor, x equals 2 plus I. So now there's 3 zeros. So then first thing we would do is put each 0 and convert it into a factor. So if x equals 1, then x minus 1 is a factor. For x equals 2 minus I, if you recall in class, talking about this topic, when you have these pair of zeros that are called complex zeros or complex roots, you want to get both of these on the same side as x, so x minus 2, and then you plus the I. So it's going to be x minus 2 plus I. And for this one, you're going to subtract the 2 and subtract the I. So then the factor is x minus 2 minus I. And then I would multiply these two factors together first. So that's going to be x times negative 2 times negative I. So those three are going to be x squared minus 2x minus ix. And then you multiply the negative 2 to all three. So that's going to be negative 2x plus 4 plus 2i. And then finally multiply the I to all three terms. That's plus ix minus 2i minus I squared. And now you have terms that cancel out. And then remember I squared is negative 1. So that's minus negative 1 right there, which is really a plus 1 combined with this plus 4. So that'll give you a plus 5, and then the negative 2x and the negative 2x is negative 4x. So that turns into x squared minus 4x plus 5. And then we have this x minus 1. So right now, p of x looks like that, and there could be a coefficient in front of there. That's where part C is going to come into play. So I'm going to just put a as some unknown coefficient. I'm going to multiply these two together by first distributing that x. So that's going to give x cubed minus 4x squared plus 5x. Now distribute the negative 1. It's going to be negative x squared plus 4x minus 5 when we combine like terms. So this is the expansion of multiplying these two together, but we still have that coefficient of a. And this is where this comes into play now. When x is equal to 0, the polynomial should equal negative 15. Right now, without this a, if all the x's were equal to 0, then the only thing left would be negative 5. So to figure out the value of a, we're going to plug this negative 15 in for p of x and 0 in for all of those variables of 0. So negative 15 equals a. And then if all these variables turn into 0, it's 0 minus 0 plus 0 minus 5, which is negative 5. If you divide both sides by negative 5, you get a is equal to 3. So then finally, and you can either leave the negative 3 outside like this, or you can multiply each term and distribute the negative 3. Really, that it doesn't make a difference. Okay, question 7. I'm going to write this first in factored form. So for part A, the vertical asymptotes, remember, are domain restrictions, and those come from the denominator. So x cannot equal 3 or negative 2. So that's where we're going to put our vertical asymptotes, 3 and negative 2. And it wants us to label, so x equals 3 and x equals negative 2. Now for part B, the horizontal asymptote, if recall horizontal asymptote, you compare the degree of the numerator to the denominator. If the numerator has a smaller degree than the degree of the denominator, which this is degree 1, this is degree 2. So the numerator has a smaller degree. In that case, the horizontal asymptote is the line y equals 0. X and y intercepts. So starting with the y-intercept here, you let x equal 0. And I'm going to go to the original form here. If x is equal to 0, all of these x variables turn into 0. We've got negative 1 divided by negative 6, which is positive 1/6. It's right about there. Now for the x-intercepts, we let y equal 0. And if you remember in class what we talked about for this kind of an equation, a rational function is only going to equal 0 when the numerator is equal to 0. So we just need to worry about what's happening here in the numerator. And that's when x is equal to 1. So the x-intercept is the point 1, 0. And then for part D, the domain, if we look at the domain restrictions, x cannot be 3 or negative 2. So those are, the domain is any real number except for negative 2 and positive 3. So we would write that as negative infinity to negative 2, and then negative 2 to 3, and then 3 to positive infinity. Now for part E, to graph the function, I'm going to start here in the middle. We see 2 points right here. And this 0 of x equals 1 came from this factor, which has multiplicity that's odd. So we know it's going to cross through and not bounds. It crosses through and looks like that. And over here on the right side, I'm going to plot some points, x equals 4 and x equals 5. So I'm going to keep track of that in a table of values here. When x equals 4, here in the numerator, we're going to get 4 minus 1, so that's 3. In the denominator, we're going to have 4 minus 3 times 4 plus 2. So 4 minus 3 is 1, 4 plus 2 is 6, 1 times 6 is 6. So we get 3 over 6, or 1/2, so 4 comma 1/2. Do the same thing for 5. 5 minus 1 in the numerator is going to give us a 4. Then here we have 5 minus 3 times 5 plus 2. So 5 minus 3 is 2. 5 plus 2 is 7. 2 times 7 is 14. So 4 14s, which is right about there, 2 7s. So you can see getting closer and closer to that horizontal asymptote. Now over here, I'm going to do a similar thing. I'm going to plot a few points on this side of the vertical asymptote. So I'm going to plot negative 3 and negative 4. So when x is negative 3 minus 1 gives us negative 4 in the numerator there. Negative 3 subtract 3 is negative 6. Negative 3 plus 2 is negative 1. Negative 6 times negative 1 is positive 6. So negative 4/6, or negative 2/3. So when x is 3, y is negative 2/3. That's right about there. For negative 4, 4 minus 1 is negative 5. In the denominator, we have negative 4 minus 3, it's negative 7. Negative 4 plus 2 is negative 2. Negative 7 times negative 2 is 14. Negative 5/14. It's right about there. So that graph looks like that. All right, part A, we're solving a logarithmic equation, natural log. The only way we can get x by itself is to cancel the natural log. The base of e cancels the natural log, but we have to isolate a few things. So I'm going to subtract a 2 and then divide by 3. So if we subtract 2, get 3 times the natural log is equal to 7. Now divide by 3. Now to get rid of that natural log, we're going to use a base e on both sides. So now we have x minus 1 equals e to the 7/3, and then finally add 1, and that's the exact form of the answer. For part B, if you recall what we talked about in class, you cannot solve a logarithmic equation if there's multiple logarithms on the same side of an equation. So first step is to condense these two logarithms using the product property. Product property says if there's a plus sign between two logarithms that have the same base, you multiply the terms inside. So it's going to be x times x minus 3. So we condense into one logarithm. Now we cancel the logarithm using, in this case, a base 10. So now we have x squared minus 3x equals 10. So this is a quadratic equation now. So if we subtract 10, because remember when you solve a quadratic, it needs to equal to 0. And we can factor this into x minus 5 and x plus 2. So we have x equals 5 or x equals negative 2. Now, remember with logarithms, the value inside a logarithm can't be negative. So if I plug negative 2 in here, log of negative 2 is undefined. So x equals negative 2 is called an extraneous solution. The valid solution, well, now we got to check 5. 5 is fine here. 5 minus 3 is 2. That's still positive. So it looks like 5 works. Question 9, part A here, we're expanding this logarithm into multiple logarithms. So we have a quotient meaning a fraction, so we need to separate the numerator from the denominator. That's done with subtraction. So it's going to be log of the numerator minus log of the denominator. Now we have a product here, x cubed times y squared, so that needs to be expanded now using the product rule. So log plus log y squared minus log z to the 4th. Now the final step here is the power property. We're going to bring down all these exponents in front of each of their respective logarithms. Now for part B, we're going backwards. We have several logarithms that we need to condense into a single logarithm. So we're going to do everything in the reverse order, starting with these numbers. These coefficients need to be written as exponents. Now I'm going to condense these two into a single logarithm. Since there's a minus sign between those two logarithms, it's going to form a quotient. So x minus 1 squared in the numerator and x plus 2 in the denominator. And now we got to condense these two logarithms. Sorry, that's a log base 2. There we go. Condense these into a single logarithm. And since there's another minus sign, this is going to be the quotient rule. See, if this were a plus sign here, then we would multiply these two expressions, so then this would end up in the numerator. If we're subtracting, that means we're forming a quotient. So this divided by this means that this is going to end up in the denominator. So we're still going to have a quotient with x minus 1 squared in the numerator. Then I'm going to take that x cubed, put it down there, and combine it with the x plus 2. All right, we're solving a variable that's an exponent, so we're going to have to cancel this base using a logarithm, but we're going to have to get that base of 3 by itself, so we're going to have to get rid of the 2 and the plus 1. So first step is to subtract 1, then divide by 2. So you're going to have the base 3 is equal to 4. Now we can cancel the base using a logarithm. And then we can add 1. Unless there are specific directions here, you're fine to leave the exact form. The question may specify here, give the exact and approximate form, but for this one it just said solve, so you're okay to leave it in exact form like that. All right, partial fractions, we're going to factor the denominator. Since there's two factors, we're going to have two partial fractions. I'm going to multiply this whole thing here by the common denominator. So when this distributes over there, then we're just left with 3x plus 1. When it distributes to the a partial fraction, the x minus 5s would cancel, so the x plus 3 distributes to the a. And then finally, when it distributes to the b partial fraction, the x plus 3s would cancel. So then it's the x minus 5 that multiplies with b. So the way this was described in class, once you have this expression now with no fractions, you can solve for a and b by using convenient values for x. We let x equal, for example, in this case, x could be negative 3, because negative 3 plus 3 is 0. 0 times a means that this whole term disappears, leaving you only b that you would need to solve for. So I'm going to let x equal negative 3. Plug negative 3 here, you get negative 9 plus 1 is negative 8. Here, a is going to disappear because that turns into 0. Here, negative 3 minus 5 is negative 8 times b is negative 8b, so b is equal to 1. So now that we've solved for b, I want to solve for a. So if I want to solve for a, that means b has to disappear. So I'm going to plug in a positive 5 for x. Because then 5 subtract 5 is 0, so b disappears. So 3 times 5 is 15, plus 1 is 16. 5 plus 3 is 8. 8 times a is 8a, and then 5 subtract 5 is 0, so b's gone on this side. That means a equals 2. So then if we plug 2 here for a and a 1 there for b, the partial fractions become 2 over x minus 5 plus 1 over x plus 3. All right, so we have an allowance. Day 1 is a penny, day 2 is 2 pennies, then 4 pennies, and then 8 pennies, and so on for 30 days. So we're going to have 1 penny plus 2 pennies plus 4 pennies plus 8 pennies. And then this is not an infinite sum because it's going to go on for 30 days. So this is a partial sum. If you remember in class, in this section, in chapter 7, we talked about two different partial sums, arithmetic and geometric. This is going to be geometric because it's doubling every time. It's being multiplied by 2. So the partial sum here, well, the expression that describes this series, or the nth term for a geometric sequence, is this. The first term is 1 penny, or 1/100th of a cent. The common ratio is 2 because it's doubling every time. So there's the nth term. If you look on the formula sheet, though, we're trying to find a partial sum of a geometric sequence, or a geometric series, rather. The partial sum of a geometric series is the sum is equal to the first term times 1 minus r to the power of n divided by 1 minus r. So we're adding a total of 30 terms because it's 30 days. So n equals 30. The common ratio is r because it's doubling every time. And the first term is 1/100th of a cent, or 1/100th of a dollar, 1 cent, 1 penny. So we have all the information we need to use this formula. The first term is 1 penny. The common ratio is 2 because it doubles every day. And then n, the number of terms, is 30 because we're adding all of this for 30 days. So this is going to be 1 minus 2 to the power of 30 divided by 1 minus 2. Now this is definitely a calculator problem. So you may find this a little hard to believe, but starting on day 1 with a penny, if you double it every day for 30 days, you end up with $10,737,000. Well, $737,418.23. Okay, Cramer's rule involves determinants. So we're going to solve for z. So z, according to Cramer's rule, is d sub z divided by d. So we need to find the d determinant. That's just the coefficients. So the determinant of a 3 by 3, I'm going to take these two columns and write them off to the right side. And then finding these 3 from the top left to the bottom right. Remember those 3 diagonal. So if I multiply those 3 numbers in that diagonal, I'm going to get a positive 1. In that diagonal, I'm going to get negative 2. In that diagonal, I would get negative 4. So now I'm going to multiply these 3 diagonals, going from the top bottom left now to the top right. The first one here is negative 1. It's negative 2 times negative 2, that's positive 4. This one's going to be negative 2. So those numbers I've got in the bottom there that are red, those add together. So 1 plus -2 plus -4. The one in blue subtracts, so subtract -1, subtract 4, and subtract -2. So 1 minus 2 is -1, minus 4 is -5, plus 1 minus 4 plus 2. This is -4 minus 4, that's -8, plus 2 is -6. So that's determinant D. Now D sub Z is a determinant where what used to be in the Z column here, these coefficients, get replaced with these three numbers there after the equal sign. So 4, -1, and 1. So the constant values after the equal sign go in place of the Z column. Everything else stays the same as it originally was. And then now we do the same thing, find the determinant. So I'm going to copy these columns over here, and then all these diagonals from top left to bottom right. It's -1, -1, and -16. This direction here is -4, +2, and +2. So the numbers in red add, the ones in blue subtract. It's -18 plus 4 minus 2 minus 2, so -14 minus 4 is -18. So D sub Z was -18. D is -6. So Z is equal to 3. And it did not ask for the remaining variables, just Z. Okay, for part A, we have this sequence here. And it's arithmetic, which means it has a common difference. In this case, the common difference is 3. So the explicit formula for the nth term of an arithmetic sequence is first term plus n minus 1 times d. So the first term is 11, and the common difference is 3. So if you simplify that, you get 3n plus 8. That's an explicit formula for the nth term. For part B, now that we have the nth term, we can find the 49th term. So a sub 49, just by using that explicit formula, that's 3 times 49 plus 8. That's 155. Now for part B, the sum of the first 49 terms of the sequence, so it's a partial sum of an arithmetic sequence, so partial sum of an arithmetic sequence on the formula sheet would be this formula. So we're adding 49 terms, so it's 49 divided by 2. The first term in the sequence was 11. The 49th term was 155. So you plug that into a calculator, you're going to get 4,067. Okay, number 15 is a binomial expansion. The nice thing about this one is they're only asking us for one specific term of the expansion, not the entire expansion. So it may be a little quicker. Starting this one, though, we could start the same way we did in class. If it's raised to the 6th power, the first thing we're going to need are the coefficients. So that's going to come from the 7th row of Pascal's triangle. So we have one more. So this is the row we're going to use to get our coefficients. If we were going to do the entire expansion, then we would use these in front of every single term, but they're only asking us to find one specific term, and it's the term that would have an a to the 3rd. So if we think about this, the first term is going to have an a to the 6th power. It would be 3a raised to the 6th power. That's the first term. We don't want that term because it's not a to the 3rd, it's a to the 6th. So this would have an a to the 6th. This term would have an a to the 5th. This term would have an a to the 4th. So it's this term right here that contains a to the 3rd. So we know it's going to be 20 as a coefficient, and then it's going to be now this term 3a raised to the 3rd power, so it's going to be 3a raised to the 3rd, and then we're going to have 2b also raised to the 3rd. Because remember, the sum of these two exponents in each term has to equal the original exponent. So this is only one term of this expansion, and it's going to have that as a coefficient. And we knew that this was the term we wanted because it's the one that contains some form of a to the 3rd. The first term would have an a to the 6th. This one would have an a to the 5th, a to the 4th, so it's this one that we want. So now we just expand just this one, so it's 20, and then 3a to the 3rd power is 27a cubed, and then 2b to the 3rd power is 8b cubed. So we multiply 20 times 27 times 8, and that's 4,320. Again, this is not the entire expansion of this binomial. This is just one of the terms that contained a to the 3rd.